Hello once again, this is Kevin from PCI. Sorry to keep you waiting for just a minute or so here. We're just about ready to get going. We'll get things going here. Sean is getting ready in the background, but I've got the PowerPoint deck here, so I'll get going with the webinar. So hopefully everyone can see my screen, and we'd like to welcome you to our session. And the title of our session today is Combining SAR and Optical Imagery for Mapping Change Detection. Just a few notes on logistics. We ask that you ask questions using the questions panel. The other thing to note is that if you're in a room with several other people, don't worry about making noise and disrupting the presentation. Your lines are automatically muted. Only we can unmute your lines if you want to ask a question over the webinar later on. You can raise your hand, or I really encourage you to type questions into the questions panel throughout the webinar to make sure that we address them towards the end of the webinar when we do Q&A. A few short words on the presenters. Myself on the right, Kevin Jones. I'm the Director of Marketing for PCI Geomatics, have been for a number of years, and have a background in remote sensing image analysis, working with not only software vendors now at PCI, but previously on the data provider side, having worked with the RadarSat program early on in my career and MDA. Sean is been with PCI for a number of years as well. He is what I certainly consider to be an expert in all of our technology, whether it's a desktop, Geomatica, or GXL, or historical air photo processing. And really what Sean is passionate about is to ensure that our customers are successful with our technology and to make sure that there's a good fit to solve a real business problem. So Sean spends a lot of time with customers in various parts of the world to make sure that they have the right tools to do the job. So the topic today is, as I mentioned, SAR and optical imagery. And what we'd like to do is get a little bit of a sense of who's in the room and what is your interest and what it is that you're working with currently. So I'm going to launch a quick little poll here. I can ask if I can ask you to indicate what it is that you are currently working with. Is it primarily optical imagery, be it medium or high resolution, or is it very high resolution, meaning sub-meter imagery? Or conversely, are you working with medium to high resolution SAR imagery, synthetic aperture radar, or are you working with very high resolution synthetic aperture radar imagery? And of course, you may be working with all of these, in which case you could tick all the boxes. We're just looking to see what it is that people are mostly working with. So we've got about 3/4 of the audience who've voted. That's fantastic. Thank you for doing that. I'm going to leave the poll open for just about 3 more seconds. I'm going to count down from 3, 2, 1. Close that out, and I'll share the results with you so you can get a sense of what the actual response was. And as you can see, there's quite a few of you who are working with medium and high resolution optical imagery. A certain number of you working with very high resolution, some with medium to high resolution SAR, and the smallest category is the high resolution radar. So just a few words on PCI for those of you who may not be 100% familiar with our technology and our company. We are a company that was born out of the satellite remote sensing world. We were created or founded in 1982 and have really continued to evolve our technology to handle many different types of Earth observation imagery. Everything from aerial to satellite, radar sensors, optical sensors, what have you. We have great software for processing the data and also doing some information extraction and analysis. And certainly we have in our latest offering the possibility to automate through open source programming language, which is Python, which is what you see here in the middle. And the reason we put it in the middle is we actually expose workflow automation at all levels of our technology. So whether you're working with a desktop version of Geomatica, or whether you're working with the higher volume production system known as GXL, really we provide you all the tools that you need to automate your workflow. And the scalability and flexibility is another interesting point, and I'll just show you this slide quickly here. In terms of production capability, there are a few different ways in which you can achieve higher levels of production. On the left, we see a scenario where perhaps we have more expensive labor resources, and we choose to take advantage of compute power to achieve high throughputs. In this case, really the solution that's tailored for this scenario is a GXL, where we can make use of parallel processing. What you see here are 3 parallel computers and a single set of instructions that are being sent by someone that's operating the what we call the job processing system, or the system that's feeding all of the work to the automatic system. On the other side of the equation, I guess, or another option to scale and have flexible deployment of our technology is essentially Geomatica. So sometimes using Geomatica in a traditional sense in terms of a thick client application on a desktop machine is very advantageous, because what that does is it provides an opportunity to build capacity. So here we think of countries maybe in Africa or different parts of the world where maybe labor isn't quite as expensive, and there's a real benefit to putting people in front of this technology so that they can improve their learning and really do a great working with the imagery. Before I hand over to Sean, or just before we get into the actual presentation on SAR and Optical, we'd like to ask you what it is that you're currently using right now. Perhaps you're an existing Geomatica customer or PCI customer. Maybe you're using ERDAS, Imagine, or Envy, or perhaps you're using open source. If you are using something else, like another piece of software that, we can't list them all here. There's quite a few software packages out there that are available in the marketplace. Let us know which one. Just in the questions box, you can type in your answer, and that way at least we have a record of what it is that you're using if it's not one of these choices here. So again, once again, 3/4 of you have voted, and I'm going to leave that open for another 3, 2, 1 seconds. I'll close that out, and I'll just quickly share that with you so you can get a sense as well. So quite a few of you are using Geomatica and Envy, a smaller number of you using ERDAS and open source, and obviously there's a large number of people who are using other software, which is in the questions panel. So thanks for participating in that. Hopefully that is useful for you. Certainly it's helpful for us to understand what it is that you're interested in learning today and how we could possibly help you. So our presentation today is going to cover a few key things. We are going to quickly go through what it means to access Landsat-8 and Sentinel-1 imagery. We have some tips on that. We have some great videos that you can find on our YouTube channel. We'll go through that pretty quickly. We'll give you a sense of what types of applications are possible in terms of combining SAR and Optical. And then we'll get into an actual live demonstration. Sean has prepared a really great demonstration of our technology where he'll actually walk you through all the different steps that are needed to achieve an operational change detection workflow that leverages both optical and SAR imagery together. There's another example at the end, and I'll let Sean get into that. So at this point, I will hand over to Sean and make him the presenter. Here we go. So take it away, Sean.
All right, thank you very much, Kevin. So as Kevin mentioned, we're going to cover a number of concepts for looking at SAR and optical imagery and performing various kinds of operational workflows and analysis. But the first thing I want to go into is just to make sure that everyone here, not everyone may be a power imagery user. So I want everyone to make sure that everyone understands or recognizes that there's a number of freely available optical and SAR repositories for accessing up-to-date and archive imagery and data. So I just also want to make sure that, or emphasize the fact that at PCI, with our Geomatica software, that we believe it's very important to support a wide variety of different sensors and different data types. So we are not really embedded to any specific data vendor or data provider. So we consider ourselves to be sensor agnostic, and therefore this allows us to support a wide variety of different sensors, and one of those areas being freely available software, which is a very important data source for a variety of research and analytical operations. So this is also going to lead into the live demonstration that I'm going to give later about how we can utilize two freely available optical and SAR resource in order to perform a change detection analysis. So within Geomatica, we have a wide variety of support for most of the popular open source or freely available data sources. So of course there's the very popular Landsat continuity mission, which is has the most up-to-date, or recently the Landsat-8 sensor, which is provided by the USGS. So this provides you with visual near-infrared, pan, shortwave infrared, thermal infrared data. And within Geomatica, we have a variety of support, everything from orthorectification to atmospheric correction, pan sharpening, analysis, and the ability to use as a reference. We have astroimagery, which its support, or its the availability of it may no longer be as free as it once was, but we still have a complete level of support for astroimagery, and it's a very important data source for a variety of mining and large-scale applications of those sorts. There's also the freely available Astro GDEM, which is a worldwide 30-meter digital elevation model, and this, of course, is fully supported within Geomatica. The SRTM 90 and 30, which is also a very popular digital elevation models, source for digital elevation model. Now that we're getting the 30-meter DEMs that are becoming more widely available worldwide, this is becoming a very, very popular source for doing elevation modeling or elevation modeling. And then recently we provided the Sentinel-1 support, which has interferometric dual pole SAR. So currently right now we support intensity and reading into the data and performing analytics with the SAR data. Pretty soon we'll be releasing our interferometric capabilities. So stay tuned for that, and we're quite excited to be releasing that in the near future. Excuse me. And then Sentinel-2, so this is the highest resolution freely, freely available optical data, and this is very high on our list to support, and this will be supported in Geomatica very soon. So there's a lot of resources available in PCI, as mentioned. We want to make sure that our user base and our community knows about these freely available sources, as they can be quite useful. So we have a lot of videos online to make it easy for you to learn how to access and download and load imagery into Geomatica. So if you go to YouTube and then you search for Geomatica download Landsat-8, and this will be the video that will show up. So it's a full step-by-step guide to walk you through the process of basically registering and downloading Landsat-8 imagery. Same thing for Sentinel-1. We also produced a video on our YouTube page here, so go to YouTube, search for Geomatica download Sentinel-1, and this will provide you a variety of or a step-by-step guide for how to access, download, and load Sentinel-1 data. Now with these two particularly, I'm just going to show you something that is, I believe, important. So if we were to take our Geomatica software, I just want to make sure everyone here knows how you can go about loading this data. So if we were to look at the Landsat-8, we can take an image. So this is exactly what you would download, would be a tar.gz file. So you can extract this with any popular extraction software such as 7-zip. And you're going to get a folder with files that are basically laid out as such. We can then take the txt file, the MTL, which is the metadata file. We can drag and drop it directly into Geomatica or into Focus. And then we can support the pan, the MS, the thermal, or load all three. And then we can basically see that we get a variety of useful data sources just from this, and there's a lot of applications that we can now do with these three sets of data sets for the Landsat imagery. Now, if we look at the Sentinel, so same thing, Sentinel comes in a zip file like this, and then when you extract it, it's going to extract to a folder. You're going to have a variety of subfolders and files. So if you want to load this into Geomatica, just simply grab the manifest.safe file, and you can drag and drop it into Geomatica. And then we support, of course, the popular calibration types in order to normalize the intensity values so that we can use it for applications such as change detection. The one that I prefer to use generally when I'm doing change detection activities is a sigma naught calibration type. And then here we get our Sentinel-1 data set. Okay, so now we're going to move on, and we're going to show just a few applications of combining SAR and optical imagery. So this is just a quick outline of a few that we thought of. There's a variety of more applications in analytics and operations that can be utilized in order to perform optical analysis, or sorry, to perform an analytics or create operational workflows. So
Sean,
one example
sorry, just to interrupt really quickly. I know we cut this part out because it was a bit long earlier today, but someone's asking about the source of the Sentinel-1 data. Can you quickly flash that up on the screen, or
Sure.
let people know where it is that slide that we took out, I guess? Or?
Absolutely. So basically the steps to download the free Sentinel-1 SAR data is you can go to the Sci-Hub. It's a part of the Copernicus project. So actually the domain did change recently, but for the most part the steps, actually they've updated their website, their portal. It's very easy to follow, very easy to work through. But basically, yeah, you can click on, or you can go to this link here. And this gives you basically a portal for accessing and downloading Sentinel-1 data, and it's very easy to do that.
Perfect. Thank you, Sean.
Okay. So going back, just looking at some of the different applications. So image visualization is a popular application. So when you're working with lower resolution imagery such as Landsat or a variety of older or even medium resolution sensors, we can often provide some improved visualization of the data by adding texture information. And this is done using a fusion process with SAR and optical imagery. So this just shows an example of the kind of result you would expect. It improves, so using fused data, so fusing SAR and optical imagery together can improve classification results, as it gives you more information about texture as well as spectral information from the optical imagery. There's also a variety of analysis, so using optical imagery and combining it with SAR, so it's often easy with SAR to look for structural changes that may not necessarily be available within the optical imagery, and then we can resort to the optical imagery to better understand what those changes might be. So in this case, we had an area of Pebble Beach right around the US Open, and this was all of a sudden set up within a couple of days, and we can then conclude that likely these are stands for audience in order to view Pebble Beach or to view this hole. And the area that we're going to be talking about in the workflow that's just going to come shortly is how to improve your automated workflows by combining your analytics from SAR and optical imagery in order to create more reliable, more robust workflows. So we're going to be showing two different examples of this. So the first example is going to be performing automatic land reclamation activities, or looking for automatic land reclamation activities. and we're going to demonstrate how we can do this and the kinds of results and how you can improve your results by cross-referencing the SAR and optical imagery. So we're going to look at now, we're going to go into our live demonstration. And I do believe that some people have questions, so I would ask that the questions, if you would like, you can type them in, or if you want, we can actually unmute you at the end of the presentation, so please hold on to your questions. And I promise we will do our best to get to them, and if we don't get to any of your questions during this session, we will keep a record of everything and we will get back to you by email. But we will do our best in the session at the end to get back to all your questions. So with this particular example that we're going to be showing you so just keep in mind that there's a variety of different applications, and we just chose this as one interesting application that we thought was quite interesting. So we're going to create an automated workflow that can identify natural and artificial land reclamation activities. So what we're trying to do in this project, we're basically looking at the requirements that it must be automated, must be highly accurate, and must be using freely available data. So what is the value of doing this? Well, one, trying to manually search for new land activities or new land reclamation activities can be very time-consuming. It doesn't happen that often, and therefore to constantly comb through imagery or go through imagery can be difficult and very time-consuming, very costly to do this. So it's very important too, because many contested artificial land reclamation activities are occurring around the world. So it may be important to your national security. It may be important to a variety of different reasons in order to identify these activities. So we want to create a system or an automated system that will continuously monitor areas by looking through different imagery in order to see when a landform may pop up or may have occurred. So one of the issues with this approach, if we were to only use optical imagery, is that we are overwhelmed with atmospheric contaminations. So here you can see as we ran the analysis previously on just using 2 Landsat images, and what we got was basically a number of false positives due to the clouds and haze in the area. However, we did get the real change, but with that, as mentioned, we got a variety of false positives. So this can be very negative because all of a sudden we're getting way more false positives than we are getting true positives, and therefore the time you'll spend just searching through the different matches that may be a positive or a false positive will sort of negate the purpose of doing an automated workflow. And same thing, issues with using only SAR is that we get also false positives when we do a change detection from ocean waves and currents, or changes in the ocean waves and currents, especially if we're working with VV polarimetry or polarimetric bands. And the reason for this is that, as mentioned, is that the VV band is very sensitive to roughness in the sea and changes to the roughness in the sea. So as a result, this can create false positives. Now, obviously, we prefer to try to use HV or HH data, which is less sensitive, but when you're trying to create an automated monitoring, continuous monitoring system, it may not be possible. You may have to work with the data you have. So by combining both the SAR and optical imagery, we can improve our results significantly. So let's take a look at the workflow. So first I'm going to show you the workflow from a more manual perspective to show you going through these steps, and then I'll run it through a Python script to show you that we can automate this. But I just want you to understand the operations that are necessary and that are involved in doing this workflow. So the first thing we're going to look at is we're going to take the Landsat-8 thermal bands, because my area of interest is the South Pacific, which is a relatively warm ocean, we can use this to highly or quite accurately mask out haze and cloud. So let's take a look at that right now. So if we look at these two thermal images, which are acquired from the Landsat imagery, we zoom out, we can see that these areas of lower values, so basically lower thermal signatures or lower temperatures, identify clouds. And obviously thicker clouds have even lower temperatures. And the haze as well is being identified in this area. So we can use this information from these two data sources in order to better extract masks for cloud and haze so that we can eliminate that from, or eliminate as much cloud and haze as possible from being incorporated into our change detection analysis. And then from doing so I used our raster calculator, but in Python we can use our modeling environment in order to basically create a cloud and haze mask from this data set. Now it's not going to be perfect, but it's going to significantly reduce the number of false positives that we get in this area. So that's the first input that we want to create, is that mask, that haze and cloud mask, which will be an input to the change detection. So now in order to do the change detection, the first things we need to do is we need to ingest the Landsat-8 multispectral and panchromatic imagery, and then we need to compute the top of atmosphere reflectance. And this is important because this will normalize the imagery to between values between 0 and 100. So once again, we'll go back to our imagery. So go to our input Landsat-8, and we're just going to take our 2015 imagery, our PAN and MS, we're going to use this, so we'll just zoom in and update the histogram so you get a better perspective of what we're looking at. And what we can do here, or the first step that we need to do here, is we need to take our input data sources and we need to perform an atmospheric correction. So I'm going to do it with the wizard, but this is available as an automated algorithm in our library. So I'm going to point to the multispectral image and the panchromatic image, as the multispectral is required to do this analysis. And then I'm going to just provide the output directory. So I'll go TOA 2015. Provide that here. So as you can see, all the settings, all the calibration information, everything is automatically calculated from the metadata of the imagery. So we don't need to set up any parameters. So really this is highly automatable. So we just click run. It's a fast process. It's going to create the top of atmosphere reflectance as well for the panchromatic and for the multispectral imagery. And I'm going to show you just very quickly why this is important. So the imagery itself isn't really going to change much. You won't notice a change visually, but if we look at a pixel value here in our top of atmosphere reflectance, we can see that it ranges, or it's around 9.5, and then we have values that basically range up to like 50. So really the values have now been normalized between 0 and 100, and we've also normalized for solar angles, for the Earth-Sun distance, and atmospheric irradiance. So basically, or sorry, exo-atmospheric irradiance more specifically. And then compare that when we look at the raw imagery, and we have values that are in the tens of thousands and the thousands of values down here. And this is because it's uncalibrated. It's a scaled DN value. And the imagery, if you're comparing from different years, different dates, they could be completely scaled using completely different calibration coefficients. And therefore, when you try to do a change detection, you really could be comparing apples to oranges instead of apples to apples. So that is the value of doing this, and this will give us a much more reliable change detection result. So really we just need the TOA, the top of atmosphere panchromatic image, So we're going to take that from the 2015 and we're top of atmosphere corrected panchromatic image from the earlier date. And as you can see, we have a significant amount of atmospheric distortions here. And we're going to perform a change detection. So now we're moving on. If we go back to our chart, we're now moving on to the change detection step of the optical imagery. So what we're going to do at this point, we're going to go to Analysis, Change Detection. And I want to show you what happens if we perform the change detection without the cloud and haze mask. So I'm going to take the top of atmosphere panchromatic image from 2015 as my working raster, and the one from 2014 as my reference. We'll compute it as a pseudo color, and we're going to click Run. So what ends up happening is, because we're doing a ranked change or a relative change, the atmospheric effects are showing up, are registering as a higher change than the new land entity. So as you can see, our change values that we're getting for the new piece of the new island that is showing up is really only in the values of 80 percentile, 70 percentile, so it's mid-range. So this would be very difficult to extract in an automated process, because how would you know what is your lower and your upper threshold? So what we want to try to do, similar to what tassel caps do, is we want to push these values to the top of the range. And by eliminating the atmospheric as much as we can, noise, we can do that. So let me show you how that's done. So all we're going to do in this case, we're going to take our cloud mask, and we're going to once again go to our change detection wizard. We're going to add the exclusion mask here. And once again, what I'm showing you here is also available as an automated algorithm in our library, so this can be added to a workflow. And let's rerun this process. So now we've excluded all the cloud areas and haze areas. And now our actual, the piece of, or the new land entity that is shown up, if you can see here, and we look down here, the values that we're getting for change are now in the high 90s or mid 90s. So they're now ranging in the upper part or upper portion of our change values. So this is much easier to automate. So we want to make sure that we're pushing these changes as like this is the majority of the change occurring in this imagery or between these images. So this becomes very easy now to extract in an automated workflow. So what we can do here, which would be the next process at this stage, or actually, sorry, before we go to that one, the next process that we're going to do here, actually, is we're going to extract the change as polygons. So this, we can go to our algorithm librarian, go to export, and we're going to go to our set up our inputs. So we can take the change layer from the optical change, and we're going to set up our threshold minimum as 95, because everything above 95 percentile is what we want. Threshold maximum we're just going to set because it's between 95 and 100. Minimum area, well, we can set this as 1,000 pixels, which means at the resolution we're working with, it's about 12.5 square kilometers, I believe. And that's it. So we're going to run this. So we're basically looking for larger land mass activities. So if we close that, we turn this off. So we can see that we've received a change polygon for the island, but we've also got still a few false positives here. So how can we further clean this up? And this is where the SAR part of the workflow comes in. So now we've computed and extracted our change for the optical. Now we can do the same for the SAR data. So the workflow is very easier. So I can go to our input Sentinel imagery. I'll bring them into the project. So we'll turn that layer off for now. And same thing. So as you can see here, what we want is to identify this new landmass as change, but we have to be careful because we have a lot of other changes occurring in ocean currents and wave and waveforms within these two Sentinel images. So what we're going to do is we're going to go to Algorithm Librarian. We're going to use another algorithm called CCD-10, which is a change detection specifically designed for SAR intensity data. And we're going to put our 2015 imagery as our input. And for our reference, we'll do the 2014 data set. So now we're going to output this as a pseudo color table. We're going to change our window size so we can provide a bit of a smoothing filter to about 15 pixels. And we can run. This will just help smooth out some of the speckle. So another important aspect of this, is, I actually don't need these ones. And we can just work with the pseudo color when that's what we want. Sorry about that. So another important aspect of doing this change is that when we inputted the SAR imagery is that we loaded it, we're first of all comparing the same polarization, so it's a VV to VV in this particular case because that was all available for this date. And another important aspect is we're using the same calibration type, so both data sets were imported with a sigma naught calibration. So what we're going to do from this is we're going to also extract this change, and as you can see, when it came to the landmass, a significant amount of change, so way up in the 99th percentile and above is where we basically have a significant amount of this change. So we're going to go back to our tools. We're going to go to that XPOL RAS to extract this change, and we're going to use the same settings for the most part, just because we can be a little bit more sensitive with SAR data. So we'll make it 98, and we'll set our input file to the ranked change for the CCD change detection. We'll run this. So if we take this off the map, we can see that while we did once again get the island, we still got a variety of false positives. So now for the last step, which is if we go back to our chart, so we just performed this step here, is now we're going to compare the change detection results between, basically do an intersection analysis between the optical results and the SAR results. And this is going to help create a more reliable result. Now there is obviously the possibility that you could have false positives covering the same area between both, but you're going to still remove a lot of extra false positives. So when we do this, I'm just going to go to one of ours and I'll just go select all. And here I can go to our spatial query and I'm going to do an intersect analysis. So it's going to select in the other layer where we have an intersection, and then I can just go save as, save the selected shape in this particular case, and I'll just call it our result. So now if we look at the result that's loaded, and all we're left with is just the real change. So what I did here is I showed you the workflows that you would go through in order to identify basically the change activity. But what's important to what's important is to also understand that what I've shown you can be automated in a workflow. So what I've also done to help illustrate that point is created a Python script that is going to basically do what I just did there, go through those same steps, and create an output change result. So we can go here. So we have our input data set up. So it's the input MS pan thermal data for the 2 Landsat scenes. The input SAR inputted with the sigma calibration for the 2 SAR scenes. We specify a minimum landmass, which is 1,000 pixels. Set our working directory where all the processing will be performed, the output directory, which will include our output file, and then our functions for running the processes. So if we go here, we can run this process, and it's quite quick because we're just working with just a few images here. So the first thing it's going through, like I showed you with the workflow, so I'll just bring this side by side. So it first goes and calculates the cloud masks from the thermal data. It then calculates the top of atmosphere for the 2 image sets. Then the next thing it's going to perform is the optical change detection. And then it should perform the SAR change detection. It just takes a few seconds to do that. Then now it's doing the CCD SAR-based change detection, so it's going through this workflow. Okay, so now it's going and it's extracting the change. So as we said for the optical, it's extracting the 95 percentile and up as valid change. And then when it goes through, so this also takes a few seconds. And then next it goes through the top 98 percentile for the SAR, as I showed. So this is the step that it's currently at. And now it should be performing, or actually this is the step. Now it's performing the intersection analysis. And it found one new result. So it's now computing the centroid for the change, and it completed the process. So if we take a look at the output, so we added the pan-sharpened image, and basically what we did for this case is just put an X or a centroid to just mark or flagged where it identified a change between the two data sets. And you can see that all the false positives were removed, and we got our change. So you can imagine how this could scale up to adding more imagery and throwing images through. And while it may not be 100% perfect all the time, it will certainly be much more reliable results because of the use of combining SAR and optical. So what I want you to take away from this is not that this particular application may not be of use to you, but to start thinking about how, especially within a change detection perspective, how utilizing optical and imagery together may give you a more reliable result and may help you automate workflows. So the other thing I want to do is also just explain, so this is our last very quick demonstration, is just another one where we basically use it to help improve coastline mapping. So the project here, the example we want to do is we want to automatically map large coastlines at high detail. And the project requirements is it must be automated, highly accurate, and high detail. So the issues with only using optical imagery is that we tend to get errors when we're creating our pixel-wise modeling methodology, where maybe very dark pixels due to terrain shadow or rock types may be mistaken as water. So by using SAR imagery, we can help identify these areas and then maybe manually or flag them for manual edit or identify a way to fix them automatically. So the workflow would be as such as that you would input your data, calculate the top of atmosphere, do a model the water using a pixel-wise modeling methodology, improve the water model using your SAR data to identify terrain shadow, extract your land polygons, and then remove the inland water bodies. So let's launch the process. So what we're going to do here is I'm basically just going to go back to coastline extraction. So just delete this. And what it's going to do is it's going to automatically go through the imagery, add the SAR imagery, and then create coastlines. And this could be scaled up, and it was actually used for a project, basically where we extracted this coastline for all of Mexico using just imagery along the coastline here, and it assembled it for them. And if we look at, so this whole coastline of Mexico at 5-meter resolution was generated in less than 36 hours. And these are basically just samples of image tiles that were used for the extraction process, or the primary extraction process. And if we look closely at the detail, you can see that we got very good detail along the coast. So this could be used for change detection to look at coastline erosion or rising water levels, ocean levels. So you can compare it year after year to see if your coastline is changing. This is just at a 1-to-1 to show you the kind of resolution and detail that we're getting. So we'll just very quickly wait for this process so it shouldn't take too long. And actually, perhaps while we're waiting, let's ask our third poll question. So I can hand it over to you, Kevin, to introduce the poll number 3.
Sorry, my line was muted there. Yeah, just asking whether you are liking what you're seeing and whether you would consider working with PCI software. Pretty straightforward question. So is it very likely, somewhat likely, not likely? Don't be shy to speak the truth. We won't hold it against you. It's important, obviously, that we know if you're interested, if you'd like to talk some more, we'd obviously be happy to do that. So I'm going to leave that open for a couple more seconds. How's your script going, Sean? Is it almost done?
It is probably another 30 seconds. Oh, no, it should be done in like 2 seconds.
Okay. So I'm going to close the poll down in 3, 2, 1.
Okay, so while we wait for it to finish, we can just actually, sorry, so now it's completed. So it took 142 seconds, and we extracted it for, whoops, this is the coastline model. So we have this area over here. So as you can see, there were 5 separate images. Completely, they're not mosaicked. And then we created this file here, which is basically an extraction of the coastline. We had some inner, so you can see the detail along here. And you can see that everything was nicely combined in order to make sure that we have a contiguous or a continuous coastline layer here. So with that, I'm going to pass over the handle to Kevin, who can open up our Q&A session, so we can now address some of the questions that you might be you're interested in asking.
Great. Thank you so much, Sean. That was a very good overview of the power of using the right tools, meaning the tools that allow you to calibrate the data so that you can perform change detection and arrive at a result that will be accurate. And hopefully everyone got the sense of the automation that can be achieved through Python, as Sean was showing there. We have some other ways of automating things as well. So we have some questions. There were a few questions, Sean, when you were doing the atmospheric correction. I don't know if you see those in the questions panel, but we have a few different people who are asking about why were you doing top of atmosphere as opposed to ground reflectance or surface reflectance, I guess, which is the same thing.
Yeah, absolutely. So the reason is that doing a complete ground reflectance, so one, we're working in a primarily water imagery where it's primarily water bodies, and the land cover is very, very minimal. So it can be very tricky to try to automate that. Generally, if you want to automate ground reflectance, you have to use an approach called the burying method, and that requires that you have a relatively large number of DDV pixels, which is known as dark dense vegetation, so of the conifer type. And obviously in this area we don't have sufficient numbers, so that method would fail. And then to just use the standard default constant values may not be reliable. So a top of atmosphere, while it may not get you the same level of accuracy as a properly run full ground reflectance correction would, it is more reliable for a automated workflow at this stage.
There's a question about change detection with land subsidence, coastal areas with depressed landscapes. I'm not sure if you have any thoughts there, Sean.
Yeah, so land subsidence, I mean, basically we are working on our interferometric SAR package that that we're hoping to release in the not too distant future. So that would be the appropriate application, and then obviously Sentinel-1 would be a wonderful data set to use for that kind of application. So yeah, it's basically right now, yeah, the proper application for assessing land subsidence would be to do interferometric SAR analysis, which we will have a very nice package coming out in the near future.
Go ahead, Sean. Sorry, you were going to pick one out of the
meantime, I'm going to address a question from an old classmate of mine. So any success in steep mountainous terrain for landslide detection? So yeah, basically one of the best things to do in this kind of application would be generating digital elevation models from high resolution satellite imagery, or at the very minimum medium resolution. There's a lot of different satellite packages available for performing that kind of analysis. The problem with land subsidence using like even interferometric SAR is that the changes are landslide detections, the changes are so significant that that basically they would become completely incoherent at that stage. So with this one, it would be probably more reliable to use optical imagery. However, also looking at intensity or polarimetric changes from polarimetric stars such as RADARSAT-2, you could also get some likely reliable results. And same thing, because also landslides, generally speaking, there might be vegetation below, and then obviously all of a sudden the vegetation is gone. So there's a variety of applications you could do in order to, or workflows you could create in order to improve the success of landslide detection.
There's a question about SAR and optical fusion. I'm not sure if you addressed that or not. What was used in terms of the algorithm? Was it pan sharpening, or was it a specific SAR optical fusion algorithm?
So there's actually a specific SAR SAR and optical fusion algorithm. I'm just going to bear with me for 2 seconds while I get the name of that algorithm. Okay, so ASMF is the name of the function used for fusing a SAR image channel with multispectral channels. So ASMF.
Okay, great.
And it's actually the full details provided on our freely available SAR training guides as well.
With that, I think I will close off the session. There's been quite a few questions coming. I think we've addressed most of them. I'd like to thank Sean. I'd like to thank you for participating today. It will be made available as a recording within the next day, and we hope to speak with you very soon.